In this video, we will look at how to write balanced chemical equations for combustion reactions using the combustion of butane gas as an example. So before we get into it, what is butane? It is a colorless gas, and its combustion actually has a number of uses and many common applications around the house and also in the laboratory. Lighters contain liquid butane under pressure, and that is converted to a gas before it is combusted to produce that flame. Bunsen burners in the lab, the gas that is supplied to these Bunsen burners is a mixture of butane as well as other short chain alkane gases, and that is what is combusted to produce the flame that we use to heat a lot of chemical reactions. Butane torches, often used in cooking to caramelize the top of a creme brulee maybe. These contain a butane gas that is obviously combusted to produce the flame. And a lot of your stovetops at home, or whether you're out camping, the gas that is supplied is often butane. Okay, so now let's look at the chemical equation behind these uses of butane. As I go through, I will write the generic steps for writing a balanced equation for any combustion reaction you might come across. Okay, so step one is to write the reactants and the products of the chemical reaction. Now in this particular example, we have a hydrocarbon in butane gas, and it is reacted under complete combustion. So that means all of the butane is converted into the two products of combustion. So let's write butane, C4H10. Do not forget to write your states. Now, any combustion reaction is a reaction with oxygen to form carbon dioxide and water. Now, because it is a complete combustion, that means we have excess oxygen, so the only two products should be carbon dioxide and water. So that is step one complete, writing the reactants and the products. Now we need to keep moving through in order to balance this equation. So step two is to balance everything in the equation except for oxygen and hydrogen. Okay, so on the left-hand side of the equation, we have 4 carbon atoms. So in order to ensure that we now balance the right-hand side of the equation, we need to place a coefficient of 4 in front of that carbon dioxide. So now our carbon is balanced. And that is the only other element in this reaction apart from oxygen and hydrogen. So that is step 2 complete. Now, step 3 is to balance hydrogen. So in order to balance the hydrogen, we first need to look at how many hydrogen atoms we have on the left. So we have 10 in our butane gas. Now over on the right-hand side of the equation, we need to use this water, put a 5 coefficient in front, and now we have 10 hydrogen atoms on the right-hand side. So that is our hydrogens balanced. And step 4, and almost the last step, is to balance oxygen. Now it should be easy to remember these steps because we always should be balancing our oxygen last. Because it is on its own, there's no other atom combined with the oxygen molecule here, So we can really put whatever number in front that we want. We don't need to worry about messing up the numbers of other atoms when we change the number of oxygen molecules. So we leave oxygen until last. So the first step is to look on the right-hand side of the equation and look at how many oxygen atoms we have on the right-hand side currently. So in carbon dioxide, we have 4 times 2, so that's 8 oxygens. In the water, we have 5 oxygens. So in total, on the right-hand side of the equation, we have 13 oxygen. Okay, so now in order to balance the left-hand side of the equation, we need to put 13 oxygens on the left-hand side. Now, what we can't do is simply put a 13 in front of oxygen, because that would mean we have created 13 times 2, which equals 26 oxygens. So what we do instead, and this is a nifty trick if you ever come across any questions similar to this one, we simply write it as 13 divided by 2, and therefore 13 divided by 2 times 2 gives us 13 oxygens. And so now we have the same number of oxygens on the left-hand side as we do on the right-hand side of the equation. Now you may be looking at that final balanced equation for the complete combustion of butane and think that it looks a bit funny, and it sort of does. So we don't normally include fractions into our balanced equations. So you can remove this fraction by simply multiplying the coefficient of every other product and reactant by 2. So I'll do this down the bottom. So if we multiply butane by 2, multiply the oxygen by 2, and that will bring us back to 13. And multiply your carbon dioxide by 2. And lastly, the water by 2 as well. Now this would be the final overall balanced equation for the complete combustion of butane gas.